Assalamualaikum and good morning. Today we'll be presenting on the topic 2, which will be the last subtopic 2 is called Anchor Earth Wall. And I will share I'll share to you the topic contents. So I believe that most of you have seen these slides on previous class. So the flexible retaining wall can be classified into two, which are embedded wall and also anchor as well. So today we'll be on the topic anchor as well, how the anchor as well is designed based on the fixed earth method than free earth method. Here you can see the topic contents such as introductions, types of anchor as well, mode of construction, stability, modes of failure, design of proper ship by wall, water pressure distribution, seepage, and the last one is the anchorage. Okay, what is an anchor as well? Anchor as well, it is used for deep excavations and they can be classified into two based on the methods of design. For example, here free earth method and the fixed earth support wall. The deep excavation is used to retain larger heights of soil compared to that of a cantilever wall. Ship pile walls need to be propped or anchored. It means that when you see the retaining wall from the front view, you might see that some sort of the tie bar was inserted into the wall to retain the soil structures behind the retaining wall. So the multi-proper or anchor ship pile walls typically used in deep excavations. However, the earth pressures behind and in front of wall always never come close to fully active or passive under working loads. Hence, they are not analyzed using limit equilibrium or classical earth pressure theories. However, single proper or anchor ship pile walls may still be analyzed without resorting to numerical or finite element method. So as you can see on the right figure, it is how to construct the proper earth wall. For example, for single proper walls, often propped near the top and they use extensively with tieback in waterfront constructions. What is the use of tiebacks? The tiebacks is high tensile steel cables or road anchors in the soil distance behind the wall. So in this figure, you can see a few anchor rods that will be installed behind the retaining wall. So there are two modes of constructions to construct the proper ship by wall. The first methods or the first modes of construction is by doing the excavation wall. It is constructed by driving a row of ship piling on the required line, followed by excavation or dragging to the required depth in front of the sheet piles. Means that you have identified a row lines of the road anchor, and then you drive in to the required depth and excavate according to the specified depth that you required. And then the second mode of construction is called as a backfill wall, constructed by partially driving in level ground and backfilling to the required height behind the piling. In terms of the stability of the proper ship pile wall, the stability by passive resistance is developed in front of the wall together with the forces in the ties of props. So the use of the prop or anchor is to provide a force that can resist any failure. So the top of the retaining wall is installed by the tie bars. It is used to provide a prop force, while you can see at the front of the wall here, it is developed a fully passive resistance in the dashed line here. Similarly for figure B. In order to check the failure of the propped sheet by wall, it can be classified into three. For example, figure A shows how the propped wall may fail in rotation at base, while B is referring how the propped sheet by wall rotates about the top, and C is a deep-seated slip. Also, this figure shows to you a similar modes of failure for different methods of design or methods of proper sheet by wall. For example, here on the left side, failure for fixed earth wall, while on the right side is a failure for free earth wall. For example, here for the fixed earth wall, it may fail in a rotation. Similarly, for the free earth, it may fail in rotation about the top. And fixed earth may fail due to the bending failure. However, the free earth may fail for the anchor pull-out. And this is, for example, deep-seated failure for the heath or for the soft soil. So this is what it says, that the line of the proper sheet by wall, and then install the anchor. In order to design the proper sheet by walls, there are two methods to design. The first one is we call as a free earth method. The second one is a fixed earth method. Okay, the designing of a single proper wall is influenced by base fixity. So the difference between the two conditions is about rotational fixity at bottom end of the wall. So look at to this bottom of the wall, how this forces the passive force, or sorry, how this prop force may act to the wall here. That's why it says that it is influenced by the base fixity. So it's occur due to the moment. The free earth method is based on the assumptions that the soil into which the lower end of the piling is driven is incapable of producing effective restraint from passive pressure to the extent necessary to induce negative bending moments. While for the fixed earth method, the piling is driven deep enough so that the soil under the line of excavation provides the required restraint against deformations and rotations. In the short, the lower end of piling is essentially fixed. So now you understand the difference between free earth method and the fixed earth method. The fixed end method is where you can see the end or the base of the pile is fixed to some depth in the soil. So it means that there is no deformations and rotations at the base of the wall. However, for the free earth method, it may induce the negative bending moments. Again here, in order to design proper sheet by wall according to the free earth method, you can see that the deflections of the wall, also the pressure distribution similarly to the bending moment. So due to the prop force A here, and then the rotation may occur at the base of wall, it may induce to the negative bending moment. But the things here, you can see that no rotational fixity at the base of wall. The first assumptions that we assume. And the base of the wall behaves like a hinge, rotate but no displacement. It means that the base here is a functions like a hinge. What is a hinge? Hinge is one boundary conditions that you allow for any rotations that may produce to the moment, but with assumptions that there is no displacement take place. And then you can see that the active earth pressure behind the entire back of the wall. So look at to the pressure distribution here, where the active earth pressure develop behind the wall, while the passive pressure distribution develop in front of the returning or in front of the proper sheet pile wall. For the fixed earth method, you can see that here by the dashed blue line and the deflections, the moment here is not zero. And then when we plot the bending moment diagram, there's a few element or the negative bending moment zone created along the proper sheet pile wall. And also here, the pressure distribution change from the free earth method. As the embedment increases, the moment fixity on the bottom end of the wall is gradually increased until a point is reached at which the base of the wall virtually behaves like a fixed end of a beam. The fixed end moment is provided by the large passive reaction acting behind the wall near its two. This is what it says, that the fixed end moment is provided by the large passive reactions acting behind the wall near its two. So, as we compared from previous free earth method, there is no passive pressure developed behind the wall. However, in the fixed end method, due to the wall has reached to the maximum depth to the fixed or to the hard layer of the soil, it is created to the zone of the passive near to the two of wall. So now you might see that differences a lot when you look at to the deflections, looking at bending moment diagrams, similarly to the pressure distribution, you can see why this one called fixed end method when the other method is called as a free earth method. This is an example. You are given a question. There are two methods used to analyze anchor sheet by walls. One is a free earth method and the other is the fixed earth method. Which of the methods assume that the depth of embedment of the wall is insufficient to provide fixity at the bottom end of the wall? Sketch and idealize earth pressure distribution and bending moment of the wall for the stated method. So by looking to the statement here, it's insufficient to provide fixity at the bottom end of the wall. So the answer is the free earth method. Okay, looking to this diagram, in order to answer the earth pressure distribution and bending moment of the wall, so these two or these three figures is referring to the free earth methods. Okay, again, this is how we can design the proper sheet by wall for free earth method. So it is assumed that the depth of embedment below excavation level is insufficient to provide fixity at the lower end of the wall. So the wall is thus free to rotate but is no displacement. The mode of failure here, we call it as a rotation about the point of application of the tie or prop. In the design, it is essential to ensure that the availability stabilizing moments exceed the disturbing moments by an adequate margin. So, moment stabilized is larger than moment disturbing. Okay, this is the idealized pressure distribution for free earth method. Again, only the active earth pressure is developed behind the wall. And the required depth of embankment D can be determined from the conditions that the algebraic sum of the factor moments about A must be 0. This, this condition yields a cubic equation in D which can be solved by substitutions of trial values. So where we can take a moment in order to solve the answer to find the embankment depth D. So the moment is considered at the A here. After the value D, the force T in the tie or prop per unit length of wall can be calculated from the conditions that algebraic sum of the horizontal forces must be 0. The bending moment can be drawn. For queer wall, it is recommended that depth or embankment depth be increased by 20% to cut against excess dragging, score or the presence of weak pockets of soil. Okay, in order to obtain the D value, but the methods depends on how the factor of safety is introduced into the calculation. So this is affected by how the lateral pressure distributions are considered. The active and passive pressure distributions on the two sides are considered separately, combined to obtain net pressure distribution. The factor of safety has been defined in terms of the passive resistance available in front of the wall, which gives rise to the stabilizing moment. The factor of safety may be design FP. So here, this is where it says that in order to find the D, the embankment depth, so we can consider by taking the factor of safety FP. The ppm is equal to passive pressure over factor of safety P. Okay, for returning wall, anchor ship by wall, the factor of safety must be larger than 1. The active pressure behind wall changes to passive near the 2. The passive pressure in front of wall changes to active near the 2. Due to the additional embankment depth arising from factor of safety more than 1 results in the reverse pressure profile which generates the partial moment fixity. Okay, again, this is how the influence of stiffness and the degree of flexibility. For flexible ship by walls, the distributions of lateral pressure tends to take place. This leads to a reduction in pressure on parts of the wall which move the most and an increase in pressure on the parts which move less. This distribution takes place as a result of arching. If stiffer walls such as diaphragm, arching is less significant. So you can see that previously for the free earth wall designs, it says that only active pressure is developed behind the wall. Similarly, for the in front of wall, only having the passive pressure. But some due to the reasons of the flexibility or degree of the stiffness of the wall here, the pressure distribution change slowly or increase due to this factor. But this is also a fact or might influence by the type of the wall. For diaphragm wall, the stiffness less influence to the pressure distributions. We go to the fixed earth method. The earth pressure distribution near the two of walls, similar to cantilever ship by walls, increase until a point is reached at which the base of the wall will virtually behave like a fixed end of a beam. The fixed end moment is provided by the large passive reaction acting behind the wall near its two. So this is how it is formed a new behavior behind and in front of the wall, and how that it acts. And how does this fixed end wall acts when subjected to the force and moment. For a proper earth wall, overall stability in terms of rotations about the prop position only applicable to free earth support conditions, where the fixed earth condition applies so long as the wall is adequately propped and also designed to resist the shear forces and the bending moments acting upon it. There is no failure mechanism relevant to an overall stability check. The fixed end moment is provided by the large passive reaction acting behind the wall near its tube. So now the passive pressure is larger compared to active pressure. Consider the prop wall under fixed end conditions and then consider horizontal force and moment equilibrium. The equations of equilibrium are almost identical to earlier equations for cantilever conditions, but with additional terms accounting for the effect of the prop force P. So the pressure distributions behind and in front of wall, as can be seen, similar for cantilever, but this time we have to include the prop force into the force equilibrium equations. In the force equilibrium equation, you can see that again how we derive the force equilibrium. It is by taking the area of the pressure diagram. For example, here the force equilibrium is due to some diagram blocks here. Half Ka gamma H plus T minus Z square half is the area of the triangle. Ka gamma of the soil times with a H from the top to this depth, D embankment depth, Z from the O to the base of wall, and then when you're deriving for all these force to all diagrams, don't forget to plus with the prop force P. And then similarly for moment equilibrium equations, the moment is equal to the force times with the arm moment. So the P force must be multiplied with the perpendicular distance. So H plus T, H plus T plus Z minus with E. So these equations creates to you three unknowns because now we don't know. For example, here the force of the tie, and then we do not know about the D. We also don't know about the Z. What do you need to know is that for the fixed earth method, there is no unique equations, but the prescribed prop force P and then need to solve the value of T and Z. Repeat with several values of P to obtain several combinations of P, T, and Z, which can ensure stability. Select the set values that is economical. This approach can be applied to the simplified pressure distribution considered earlier for the cantilever wall. Okay, remember when we use the prop anchor or we use the cantilever wall, purposely is to retain soil from movement. So the soil can be considered, or by taking the weight, we can have weight of soil. For example, for dry soil or for park soil, and also sometimes soil also have additional weight which come from the water pressure, or we call here is a water table. So the first conditions, when you have the returning wall, where the sites having some sort of the water level conditions. So first condition is referring to the case where the water tables levels similar on both sides, behind of the wall and also in front of wall. The water level is at the same height. And then it's great to the hydrostatic pressure. For these conditions, the hydrostatic pressure is similar for both sides, in front and back of wall. Therefore, we can cancel out the hydrostatic pressure. It means that do not include in the calculations. So it will be simplified for these conditions 1, where the water table at the same level. For the condition 2, for the water pressure distributions, it is the case where the water level is not similar behind the wall and also in front of the wall. And do not to forget about the flow net diagram. Water table levels different on both sides of wall, so the distribution, water pressure distributions unbalanced, can be rigorously determined from flow nets. An approximate solution based on assumptions that total heat is dissipated uniformly along back and in front wall surfaces between two water table levels. So the maximum net pressure occurs opposite the lower water table level. So the UC can be calculated from the equations 2BA. What is a B? B is the water table in front of the wall multiplied by water table level behind the wall, or the vertical height from the water table measured in front of wall to the water table height at the back of the wall, over 2B plus A times water pressure unit weight, or we call it gamma water, equal to 9.81 kilonewton per cubic meter. Water pressure distribution for the condition 3, it is the conditions where the depth of water at the sea in front of wall okay, right now you can see some conditions here. The water level may rise to the some depth of sea. This is condition some sort of this ocean, for example. So you want to construct a prop wall, for example, for purposely reclamation area. So for these conditions, what do you need to do to consider the water pressure effect? You have to approximate distribution DEF. GEFG may be used by calculating the water pressure UG by consider the flow net diagram here. The flow net diagram is presented by the equation 2B plus C times A over 2B plus C plus A. All this one multiplied by 9.81. So what is the A? A is the height from water level surface to the water level behind the wall. C at the depth of water in front of the wall. And B is the height of the depth or is the depth of the level from the conditions in front of wall to the toe of the prop wall. Conditions 4. Wall constructed mainly in a soil of highly permeability, and the lower part of wall penetrates a clay layer of low permeability. Assume undrained conditions in the clay. The pore pressure in the overlaying soil would be hydrostatic, so the net pressure distribution would be H, J, K, and L. So low permeability here we can consider as a clay, and high permeability here we can consider it as a sand, for example. And then this prop wall installed until mid to the penetrate at the layer of low permeability, but it is constructed in a high permeability of the soil. So the water pressure diagram generated, as can be seen here, from the zone H, J, K, and L. So it produced to you a trapezoidal net pressure distributions. For the next condition 5, the wall constructed in a clay which contains thin layers of fine sand or silt. Assume that sand or silt allows water at hydrostatic pressure to reach the back surface of wall. So it is implies pressure in excess of hydrostatic in front of wall. The consequent upward seepage in front of the wall generated. So this will be complex conditions where you can see that development of the upward seepage in front of the wall. This arrow head indicate to you the upward seepage at the in front of the wall, and then right now is that non-uniform of the retaining soil behind the wall, which consists of the clay, sand or silt here, and then followed by clay and underlays by sand or silt. So the net pressure distribution diagram plus with the seepage conditions. Okay, we go to one example for the anchor sheet pile wall is constructed by driving a line of pile into a soil for which the saturated unit weight is 20 kN per cubic meter a unit weight. So these are the soil parameters you are required to determine the depth of embankment for effective of safety, 2 with respect to cross passive resistance and the force in each tie rod. Okay, again you have to calculate the active coefficient and also the passive coefficient 0.27, 3.7, and again 1, 2, 3, 4, 5, and 6 are pressure diagram in front of wall and back of wall respectively. By taking the area of the diagram to all 6, you can have these equations. Similarly, arm or the moment distance taking for example here, figure number 1, 1.83. How do we get 1.83? So the moment is taking at the A point, And then by using the cubic equations, so you can get that the D is 4.9 meter. So depth of penetration 1.2 times D. So where they get the 1.2 here is back to our assumptions in the cantilever. So the algebraic sum of forces for D is for the D 4.9 meter is, as you can see here, the total force, and the tie force is a 98.5 kilonewton per meter, and the force in each tie rod is equal to 2.6 kilonewton. So this is the conditions for the seepage pressure for the steady seepage, and the last one is anchor ridge. And thank you.